emergency situation occurs, you should be prepared to respond quickly and correctly. Furnaces have unique problems, some of which may be detected only in the field. Correct diagnosis of the problem as well as quick response is important. In this segment of the program, we'll consider both the symptoms and solutions to these common operating problems. Let's start with flame impingement. Flame impingement occurs when the flames are actually touching the metal surfaces inside the furnace, usually the tubes. This contact weakens the metal and can quickly plug up a tube with coke deposits. Flame impingement can sometimes be corrected by adjusting the position of a burner or by pinching back the fuel supply to the problem burner. If these adjustments don't correct the situation, it may be necessary to remove the burner for cleaning or repair. A hot spot in a furnace is an area that has become overheated due to an improper distribution of heat or flame impingement. Hot spots may occur on the tubes, the refractory, or even on the outside skin of the furnace. They're a problem because they compromise the strength of a metal and cause coke deposits. Some hot spots can be detected with the human eye as a glowing red spot on the metal. In other instances, special heat-sensing instruments such as a pyrometer or an infrared scanner are used to detect hot spots. Sometimes hot spots on the furnace tubes can be corrected by redistributing the process flow so that the hotter pass of tubes receives more charge. The increased flow of charge absorbs more heat and carries it away from the hot tubes. In other situations, it may be necessary to reposition a burner or remove it from service. Another common furnace problem is the buildup of coke in the tubes. A certain amount of coking occurs naturally due to the presence of carbon particles in the process flow. High temperatures, however, aggravate the problem by increasing the amount of carbon deposits. The coke acts as an insulator, so less heat is transferred to the process flow and more heat accumulates in the metal tube. If the coking is severe, the tube may eventually rupture due to the excessive temperatures. A furnace can be decoked by injecting superheated steam and air through the tubes. This operation burns off the coke and cleans out the tubes. A disadvantage of this operation is that it interferes with the ongoing processing because the process flow must be removed from the tubes during cleaning. In furnaces which burn oil, an ash deposit or soot gradually accumulates on the outside of the convection tubes. These deposits must periodically be removed because they interfere with heat transfer. Some furnaces are equipped with stationary soot blowers, which are long tubes that run through the convection section. Steam is circulated through holes in the soot blower to blow off any accumulations of soot. A second type of soot blower is the retractable type. It's a steam lance that is taken out of the furnace when not in use. This type of soot blower can be programmed to automatically blow selected tubes in any given sequence. Soot blowing can be done while the furnace is in operation. However, it may be necessary to completely open the damper to prevent the steam and falling soot from snuffing out the flames. It's important to closely monitor and maintain the excess oxygen and draft during soot blowing. Furnace equipment like pumps, fans, valves, and burners can and does occasionally fail. When this happens, an operator must be prepared to respond quickly to prevent damage to the furnace or a possible accident. The feed pump circulates the process flow through the furnace. If this pump fails, the circulation will stop and the furnace will immediately start to overheat. This can damage the tubes and refractory and cause severe coking. Your first reaction should be to restart the pump if possible or go to a spare. If you can't get the flow started immediately, you'll need to stop the input of heat by cutting off the fuel to the burners. The damper should be open fully to allow the maximum amount of heat to leave the furnace. And steam should be added, which will have a cooling effect on the furnace. By cutting off the fuel and removing as much heat as possible, you minimize the chances of furnace damage. Once the situation stabilizes, you would want to call in maintenance and have the defective pump repaired. A second type of equipment failure is a fan failure. If one of the fans in a balanced or induced draft furnace fails, this will result in a loss of draft. If the furnace is equipped with natural draft air doors, the flame safety system will automatically open the doors, and it may be possible to keep the furnace operating at a reduced load. Some furnaces are equipped with steam rings that discharge steam into the furnace in the event of a fan failure. The hot steam rises upward and creates enough of a draft to allow continued operation. But if air doors or steam rings are not available, the safety system will automatically cut off fuel to the burners and the furnace will have to be shut down. A valve failure is a third type of equipment problem. If the valve is controlling the process flow, it will usually fail open or become stuck in one position. In either case, you won't be able to adjust the rate of flow. If a bypass valve is available, you may be able to avoid a shutdown by routing the flow around the failed valve. When a valve in the fuel system goes down, it usually fails in the closed position. This stops combustion in the furnace and means a shutdown. The furnace burners can also break down. Burner failures are often caused by plugging or fouling in the burner tip. If a burner fails, you'll need to remove it from service for cleaning or repair. Instrument failure is not always easy to detect. The operator must understand the interaction of variables in the furnace to judge whether a particular reading is accurate. If the furnace has automatic controls, the controls may try to correct a situation which doesn't exist. If this happens, the operator must take the controls off automatic and manually adjust the operating variables. Correct diagnosis and quick reaction can often prevent a furnace shutdown. Let's consider an example. In an automatic system, the controller adjusts the fuel flow to the burners based on the outlet temperature of the charge. Now, if the measuring or transmitting instrument sends out a faulty low temperature signal to the controller will automatically increase the flow of fuel to the burners, trying to compensate for the apparent decrease in outlet temperature. This in turn will cause the furnace to overheat and could cause coking in hot spots. If the operator suspects this is occurring, he can check the individual outlet temperatures for each pass of tubes. If these are above normal, this would indicate that the measuring or transmitting device has probably malfunctioned. The operator would then manually control the amount of fuel to the burners to prevent the furnace from overfiring. Another furnace problem is flameout. This is a situation where the burner flames go out, but the fuel is still entering the burners. When it happens, there is a dangerous buildup of unburned fuel in the furnace, which poses a threat of explosion. So the furnace must be immediately shut down and purged. A flameout can be caused by several things, such as a loss of draft, too much fuel, or not enough oxygen entering the air registers. In a situation where oxygen is decreasing and the amount of combustibles is rising, it may be possible to correct the problem before a flameout occurs. This can be done by decreasing the flow of fuel to the burners, opening the damper to increase draft, or by opening the air registers to increase oxygen. But if you're unsure how much uncombusted fuel is in the furnace, the safe thing to do is proceed with a furnace shutdown.